Let's now look at properties of logarithmic functions. We define the function f of x equals ln of x as the inverse of the function y equals e to the x and called it the natural logarithm. By inverse, we mean that the natural log of e to the k equals k for any value of k. Likewise, e to the natural log of k equals k. In other words, these two functions undo each other. Let's look at additional properties of logarithms. The first is that the natural log of a times b equals the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b. Thirdly, the natural log of a to the p equals p times the natural log of a. This is going to be our most important property. This is how we will get variables out of the exponent in exponential functions. Using this property, let's look at some examples. First, let's solve 2 to the x equals 5. To get out our variable x, which is in the exponent, we need to take a logarithm. To keep our equation balanced, we need to take the natural log of 2 to the x and the natural log of 5. Our property allows us to simplify the left-hand side as x times the natural log of 2. Now to solve for x, we simply need to divide by natural log of 2 to get x equals the natural log of 5 divided by the natural log of 2, which is roughly 2 to the 3.22. In our next example, let's solve 3 times 2 to the x equals 5. The difference in this example is that we have multiplication by 3 on the left-hand side. Let's make this equation look more like the one we just solved by dividing by 3 to get 2 to the x equals 5 over 3. Now, following the same steps, we'll take the natural log of both sides to get at x. The natural log of 2 to the x equals natural log of 5/3. Using our property, the left-hand side simplifies to x times the natural log of 2, while the right-hand side is still natural log of 5/3. Finally, to solve for x, we just need to divide by natural log of 2. So x equals the natural log of 5/3 divided by the natural log of 2, which is roughly 0.737. In our third example, we'll look at what to do if we have our variable x in the exponent of both sides. Again, our only tool to get at the exponent is to take the natural log. Taking the natural log of both sides, we get natural log of 2 to the x equals natural log of 3 to the x plus 1. Using our property, the left-hand side simplifies to x times the natural log of 2, while the right-hand side simplifies to our exponent, x plus 1, times the natural log of 3. We now need to solve this linear equation for x. So we will distribute natural log of 3 on the right-hand side to get x times the natural log of 3 plus 1 times the natural log of 3. Then, we will move everything with x in it to the left-hand side by subtracting x times natural log of 3 from both sides. Factoring out x, the left-hand side becomes x times the natural log of 2 minus natural log of 3. Finally, we will divide both sides by natural log of 2 minus natural log of 3 to get that x equals the natural log of 3 divided by the natural log of 2 minus the natural log of 3, which is roughly negative 2.71. Let's apply this property to another example. Recall that the radioactive element cobalt-60 loses 13.5% of its mass each year. If we start with 250 grams of cobalt-60, how long until we have half as much as we started? The phrase, how long, is saying find T, with the condition that the amount, P of T, is 1/2 of what we started. Since we started with 250 grams, we want to find T so that P of T equals 125. Recall that we found the model for P of T to be 250 times 0.865 to the T. The 250 coming from our original amount, 8.65 coming from the fact that we lose 13.5% each year, in our variable T. So we want to solve 250 times 0.865 to the T equals 125. We start by dividing both sides by 250. So 0.865 to the T equals 1/2. Then, to get at our exponent T, we'll take the natural log of both sides, to get that the natural log of 1/2 equals the natural log of 0.865 to the T. Using our property, this simplifies to T times the natural log of 0.865. Now, to solve for T, we just need to divide by the natural log of 0.865 to get T equals the natural log of 1/2 divided by the natural log of 0.865, which is roughly 4.78. So after 4.78 years, cobalt-60 will decay in half. Let's revisit our example by asking the question, how long until there is half as much cobalt-60 as at the start? Notice here, we're not saying how much we started with. Still, the phrase how long is saying find T. Here, we want to find T so that P of T equals 1/2 P naught, our starting amount. Since we don't know the starting amount, the model for P of T is P of T equals P naught times 0.865 to the T. And we want to know when this equals P naught over 2. As we did when P naught was 250, we'll divide both sides by P naught. On the left-hand side, we're left with 0.865 to the T, while on the right-hand side, we have 1/2. This equation we solved in the previous example, and we found that T equals the natural log of 1/2 divided by natural log of 0.865, which is roughly 4.78. So after 4.78 years, cobalt-60 will decay in half. Notice, with exponential decay, the amount of time it takes to have half as much as at the start does not depend on how much there is at the start. This amount of time is called the half-life. We say that the half-life of cobalt-60 is 4.78 years. To be more formal, let's define the amount of time it takes for a substance to decay exponentially to half its original amount as the half-life. Similarly, for exponential growth, the amount of time it takes for a substance to grow exponentially to twice its original amount is the same no matter how much we started with, and we call this the doubling time.